This is an audio recording for visually impaired students from the book Essentials of Physical Chemistry by S. Chan. Distribution law. If we take two immiscible solvents A and B in a beaker, they form separate layers. When a solute X, which is soluble in both solvents, is added, it gets distributed or partitionated between them. Molecules of X pass from solvent A to B and from solvent B to A. Finally, a dynamic equilibrium is set up. At equilibrium, the rate at which molecules of X pass from one solvent to the other is balanced. Distribution of solvent X between solvent A and B is concentration of X in A upon concentration of X in B is equal to A, which is a constant. For example, the following result from the distribution of succinic acid between ether and water illustrate the constancy of the ratio of the concentration in each layer. Statement of Nernst distribution law. Nernst 1891 studied the distribution of several solutes between different appropriate pairs of solvent. He gave a generalization which governs the distribution of a solute between two non-miscible solvents. This is called Nernst distribution law or Nernst partition law, or simply distribution law or partition law. If a solute X distributes itself between two immiscible solvents A and B at constant temperature and X is in the same molecular condition in both solvents, then concentration of X in A upon concentration of X in B is equal to Kd. If C1 denotes the concentration of the solute in solvent A and C2 the concentration in solvent B, Nernst distribution law can be expressed as C1 upon C2 is equal to Kd. The constant Kd, or simply K, is called the distribution coefficient or partition coefficient or distribution ratio. Then there are some numericals based upon distribution law. Solubilities and distribution law. When a solute is shaken with two non-miscible solvents at equilibrium, both the solvents are saturated with the solute. Since the solubility also represents concentration, we can write the distribution law as C1 upon C2 is equal to S1 upon S2 is equal to Kd, where S1 and S2 are the solubilities of the solute in the two solvents. Hence, knowing the value of the distribution coefficient Kd and the solubility of solute in one of the solvents, the solubility of solute in the second solvent can be calculated. Explanation of distribution law. This is an equilibrium law. When the distribution of the solute X has reached dynamic equilibrium, the rate R1 at which molecules of X pass from solvent A to B is proportional to its concentration C1 in A. The rate R2 at which molecules of X pass from solvent B to A is proportional to its concentration C2 in B. Also, at equilibrium, the rate of migration of solute from one solvent to the other is equal. Thus, we have at equilibrium, the number of molecules of X passing from solvent A into B is proportional to its concentration in A and vice versa. Also, the rate of migration of solute molecules from A to B and B to A is equal. R1 is directly proportional to C1, or R1 is equal to K1 into C1, where K1 is a constant. Again, R2 is proportional to C2, or R2 is equal to K2 into C2, where K2 is a constant. Since at equilibrium R1 is equal to R2, K1 into C1 is equal to K2 into C2, or C1 upon C2 is equal to K2 upon K1 is equal to Kd, or C1 upon C2 is equal to Kd. This is Nernst distribution law equation. Since K1 and Kd are constants at the same temperature, the distribution coefficient Kd is also constant if temperature is fixed. Limitations of distribution law. The conditions to be satisfied for the application of the Nernst distribution law are: first, constant temperature. The temperature is kept constant throughout the experiment. Second, same molecular state. The molecular state of the solute is the same in the two solvents. The law does not hold if there is association or dissociation of the solute in one of the solvents. Third, equilibrium concentrations. The concentrations of the solute are noted after the equilibrium has been established. Fourth, dilute solutions. The concentration of the solute in the two solvents is low. The law does not hold when the concentrations are high. Fifth, non-miscibility of solvents. The two solvents are non-miscible or only slightly soluble in each other. The extent of mutual solubility of the solvents remains unaltered by the addition. How is distribution law modified by change in molecular state? It was pointed out by Nernst that C1 upon C2 is constant only if the solute exists as simple molecules in the two solvents. If the solute undergoes association or dissociation in one of the solvents, it is found that C1 upon C2 is not constant. In these cases, distribution law applies only to that part of the solute which is present as simple molecules. First condition, when solute undergoes association. Suppose the solute is present as simple molecules X in solvent A. In solvent B, n molecules of X associates to form Xn molecules, assuming that a few single molecules X are also present in solvent B. The equilibria that exist in the two solvents are shown in figure 18.3. Let C1 be concentration of X in solvent A. C3 be concentration of X in solvent B. C2 be concentration of Xn in solvent B. Applying distribution law to the equilibrium, X in solvent A is in equilibrium with X in solvent B. We have C1 upon C3 is equal to Kd. Applying the mass law to the chemical equilibrium, Nx is in equilibrium with Xn. Therefore, x raised to power n upon xn is equal to kc, or C3 power n upon C2 is equal to kc. Taking nth root on both sides in equation second, C3 upon root n C2 is equal to root n kc. Dividing equation 1 by 3, C1 upon root n C2 is equal to Kd upon root n Kc is equal to K, a constant. Thus, when association occurs in one solvent, the distribution equation is modified as C1 upon root n C2 is equal to Kd. Since the solute exists largely as associated molecules, the total concentration of X determined experimentally in solvent B is taken as the concentration of the associated molecules Xn. The constant value of partition coefficient now arrived at suggests that benzoic acid is associated into double molecules in the benzene layer. Second condition, when solute undergoes dissociation. Suppose the solute is present as normal molecules X in solvent A and it dissociates into A plus B in solvent B. The equilibria set up in the two solvents are shown in figure 18.4. Let C1 be the concentration of X in solvent A and C2 the total concentration of X dissociated and undissociated in solvent B. If the degree of dissociation in solvent B is X, then X is in equilibrium with A plus B, where X के mole have 1 minus X, A has the moles X and B X. Hence, the concentration of the undissociated or normal molecules in solvent B is C2 1 minus X. Applying distribution law to normal molecules in the two solvents, C1 upon C2 into 1 minus X is equal to Kd. This is the modified distribution law equation when there is dissociation in one of the solvents. A case of this type arises in the distribution of a weak acid, example succinic acid or oxalic acid, between ether and water. C1 and C2 can be determined by direct titration of the two layers against standard alkali solution. The value of X can be found by measuring electrical conductance of solution in solvent B. Henry's law, a form of distribution law. Henry's law states at a constant temperature, the solubility of a gas in a liquid is proportional to the pressure of the gas above it. Henry's law may be mathematically expressed as C is equal to Kp, where C is the solubility or concentration, K is a constant, and P is the pressure of the gas. K is called Henry's constant. Explanation. Henry's law is in fact a form of distribution law. If a vessel containing a liquid and a gas is shaken at equilibrium, the gas can be regarded as distributed between the liquid phase A and the space above phase B. The influence of partial pressure on solubility is utilized in making carbonated beverages like beer, champagne, and many soft drinks. So-called soda water is bottled under a carbon dioxide pressure of about 4 atm. When the bottle is opened to the air, the partial pressure of CO2 above the solution is decreased about 0.001 atm and CO2 bubbles out. Let C1 be the concentration of the gas in phase B, C be the concentration of the gas in phase A. Applying the distribution law, C upon C1 is equal to Kd, a constant. We know that molar concentration of a gas is proportional to its pressure P. Hence, C upon P is equal to K, a constant, or C is equal to K into P. This is Henry's law equation. Like distribution law, Henry's law holds good for dilute solutions of gases which do not react with the solvent. If a mixture of gases is in contact with a liquid, the partial pressure of an individual gas, not their total pressure, determines the mass of each gas dissolving. In such a case, the solubility of each gas is proportional to its partial pressure. Determination of equilibrium constant from distribution coefficient. Distribution law helps in determining the equilibrium constant of a reaction when one of the reactant is soluble in two non-miscible solvents. Let us illustrate by taking example of the reaction when potassium iodide reacts with iodine to form potassium triiodide. Ki plus I2 is in equilibrium with Ki3. This reaction can be carried in water while iodine is soluble in both water and benzene. Procedure. First, to find the distribution coefficient of I2, iodine is shaken with water and benzene in a bottle. The concentration of iodine in the two layers is then determined by titration against standard thiosulfate solution. Thus, concentration of I2 in water upon concentration of I2 in benzene is equal to K, distribution coefficient. Second, to find the equilibrium constant using the value of K. A solution of Ki of concentration A is shaken with the iodine in a bottle. To this is added some benzene and shaken. On standing, the mixture separates into two layers. The equilibria that are set up are shown in figure 18.7. The concentration of iodine is determined in the two layers by titration against standard thiosulfate solution. Let B be the concentration of I2 in benzene layer. C be the concentration of I2 in water layer, which is really the total of the concentration of free I2 and Ki3. K is the value of distribution coefficient of iodine between water and iodine as determined earlier. Thus, concentration of I2 in water upon concentration of I2 in benzene is equal to K. Therefore, concentration of I2 free in water layer is equal to K into B. Hence, concentration of Ki3 in water layer is equal to C minus Kb. Therefore, concentration of Ki in water layer is equal to A minus C minus Kb is equal to A minus C plus Kb. We can now say that equilibrium constant of the reaction I2 plus Ki in equilibrium with Ki3 is Kc is equal to Ki3 upon Ki into I2 is equal to C minus Kb upon A minus C plus Kb into Kb. The square brackets denote concentration in water layer. Since all the quantities on the right hand side are known, the equilibrium constant Kc can be calculated. Study of complex ions. If the value of Kc comes out to be constant by taking different concentrations of Ki and I2 to start with, it proves the existence of Ki3 or the complex ion I3 negative. I2 plus I negative gives out I3 negative. The distribution law is, therefore, helpful in the study of complex ions. Other examples of complex formation are CuSO4 plus 4NH3 gives out CuSO4.4NH3 or CuNH3 4 2 positive and SO4 2 negative. C6H5NH2 aniline plus HCl gives out C6H5NH3 positive Cl negative, that is anilinium chloride. Extraction with a solvent. The extraction, removal by a solvent of an organic substance from an aqueous solution is probably the most important application of distribution law. The process is carried by shaking the aqueous solution with an immiscible organic solvent, say ether, ethoxy, ethane, in a separatory funnel. The distribution ratio being in favor of ether, most of the organic substance passes into ether layer. On standing, the aqueous and ether layer separate in the funnel. The lower aqueous layer is run out, leaving the ether layer behind. This is then transferred to a distillation flask. Ether is distilled over while the organic substance is left as residue in the flask. If desired, the process may be repeated with aqueous layer left after the first extraction with a fresh quantity of the solvent. The other common solvent used for extraction are hexane, benzene, chloroform, acetone, carbon disulfide, etc. The greater the distribution ratio it is in favor of the organic solvent, the greater will be the amount extracted in any one operation. Multiple extraction. The process of extraction when carried with the total amount of the given solvent in a single operation is referred to as simple extraction. To recover the maximum amount of the substance from aqueous solution, the extraction is made in two or more successive operations using small portions of the solvent provided. This is called multiple extraction or multi-step extraction. In such a process, the aqueous solution is first extracted with a portion of the solvent in a separatory funnel. The aqueous layer from which some substance has been removed and then transferred to another funnel. This is shaken with a second portion of the solvent. Similarly, the aqueous layer from the second extraction is treated with the third portion of solvent and so on. Why multiple extraction is more efficient? The fact that is more efficient to use a specified volume of solvent in small portion rather than one whole may be illustrated in a simple way. Suppose we have 100 ml of aqueous solution containing 8 grams of an organic substance. We can extract the substance with ethoxyethane. Its distribution ratio being twice in favor of ether, we are provided with 100 ml of ether which may be used in one lot or in two portions of 50 ml each. First, using all the ether in one lot. Let x grams be the weight of the substance extracted in the solvent layer, then the amount of substance left in the water layer is equal to A minus x grams. Therefore, concentration in ether layer is equal to x upon 100. Concentration in water layer is equal to A minus x upon 100. C in ether upon C in water is equal to K, distribution law. Therefore, x upon 100 divided by A minus x upon 100 is equal to 2. Hence, x is equal to 2 upon 3a. Thus, 66% of substance is extracted. Second, using two 50 ml portions of ether. Let x1 grams of substance be extracted in the first operation with 50 ml ether. Thus, concentration in ether layer is equal to x1 upon 50. Concentration in water layer is equal to a minus x1 upon 100. C ether upon C water is equal to 2, or x1 upon 50 upon a minus x1 upon 100 is equal to 2. Hence, x is equal to 1 by 2a. Therefore, 50% of substance is extracted. The substance left in water layer is 1 upon 2a. Let x2 grams be the substance removed from the water layer when it is extracted with another 50 ml portion of ether. Hence, concentration in ether layer x2 upon 50. Concentration in water layer is equal to 1 upon 2a minus x2. x2 upon 50 divided by 1 upon 2a minus x2 upon 100 is equal to 2. Hence, x2 is equal to 1 by 4a. Therefore, 25% of substance is extracted. Thus, 75% of substance is extracted by using two 50 ml portions of the solvent as against 66% when 100 ml solvent is used in one lot. Similarly, it can be shown that by using 4 to 50 ml portions of ether, it is possible to extract 80.2% of substance. 5 to 100 ml portions of ether would likewise remove 83.8%. It is clear from above that it is more advantageous to use a given quantity of the solvent in as many portions as conveniently possible. It must be understood, however, that it is not possible to remove the whole of the dissolved substance, however large the number of extraction may be. Every time the substance distributes itself between the two solvents, and a quantity, howsoever small, must always be left behind. General formula for substance left unextracted. Suppose V ml of an aqueous solution contain A grams of an organic substance. This solution is extracted with V ml of the given organic solvent at a time. First extraction. Let x1 be the substance left unextracted in aqueous solution in the first operation. Now, concentration in aqueous layer is equal to x1 upon capital V. Concentration in solvent is equal to a minus x1 upon small v. C in water upon C in solvent is equal to K, distribution law. Thus, x1 upon capital V divided by a minus x1 upon small v is equal to K. Hence, x1 is equal to a into kV upon kV plus small v. Second extraction. Let x1 be the substance left unextracted in the aqueous layer in the second extraction made with fresh V ml of solvent. Now, concentration in aqueous layer is equal to x2 upon capital V. Concentration in solvent is equal to x1 minus x2 upon small v. Substituting the values of concentration in the distribution law equation, x2 upon capital V upon x1 minus x2 upon small v is equal to K. Hence, x2 is equal to x1 into kV upon kV plus small v. Substituting the value of x1 from equation 1. x2 is equal to a into kV upon kV plus small v into kV upon kV plus small v is equal to a into kV upon kV plus small v whole square. Third, nth extraction. Following the above procedure for first and second extraction, the amount of substance left unextracted xn in the nth extraction would be xn is equal to a into kV upon kV plus small v whole power n. This general formula enables the calculation of the amount of substance left unextracted after a specified number of extraction with small v ml portion of the solvent each time. Fourth, extraction with whole lot of solvent. If the entire quantity of the given solvent is used for a single extraction, the amount of substance unextracted x dash would be x dash is equal to a into kV upon kV plus n small v. Since the quantity within the bracket is less than unity, xn is smaller than x dash. Also, xn will be smaller the greater the value of n. Hence, it is more economical to use the solvent in small portion in a number of extractions. Liquid chromatography, partition chromatography. This is a versatile and widespread technique for separation of a mixture of small amount of organic substance. The operation is carried in a glass tube packed with an inert solid material silica soaked in a solvent A water. The mixture paste is applied to the column top with then a layer of another immiscible solvent to hexane is allowed to flow down the column. A film of solvent 1 held by the silica forms the stationary liquid phase, while the running solvent 2 the mobile liquid phase. Each component of the mixture distributes itself between the stationary liquid phase and the mobile liquid phase. Thus, Cs upon Cm is equal to Kd, where Cs is equal to concentration in stationary liquid phase and Cm is equal to concentration in the mobile liquid phase. Different components in the mixture have different distribution coefficient. They pass into the mobile phase in order of their distribution coefficients. The component, say S2, with higher distribution coefficient is extracted, eluted first and is the first to move down the column. The location of the components is easy if these are colored. Otherwise, they are visualized with the help of locating agent. The portion of the solvent or band containing each component is received in a separate vessel and the solute recovered from it by distillation. Application of distribution law. There are numerous applications of distribution law in the laboratory as well as in industry. Here we will discuss some more important ones by way of recapitulation. First, solvent extraction. This is the process used for the separation of organic substances from aqueous solution. The aqueous solution is shaken with an immiscible organic solvent such as ether or benzene in a separatory funnel. The distribution ratio being in favor of ether, most of the organic substance passes into the ethereal layer. The ethereal layer is separated and ether distilled off. Organic substance is left behind. The process of extraction is more efficient if the solvent is used in a number of small portions than in one whole lot. Thus, multiple extraction is preferred to simple extraction. The multiple extraction is also the basis of the industrial counterflow solvent extraction. A dilute solution of the substance enters at the top of column or tower. At the same time, the extracting solvent enters at the bottom as the aqueous solution and the solvent pass each other. The solute distributes itself in favor of the solvent. Since the process of extraction is repeated many times at different levels in the tower, maximum quantity of substance is removed in the solvent. Second, partition chromatography. This is a modern technique of separating a mixture of small amounts of organic materials. A paste of the mixture is applied at the top of a column or of silica soaked in water. Another immiscible solvent, say hexane, is allowed to flow down the column. Each component of the mixture is partitioned between the stationary liquid phase water and the mobile liquid phase hexane. The various components of the mixtures are extracted by hexane in order of their distribution coefficients. Thus, the component with the highest distribution coefficient is first to move down the flowing hexane, which is collected separately. Similarly, a component with a lower distribution ratio comes down later and is received in another vessel. Third, desilverization of lead. Parkes process. When molten zinc is added to molten lead containing silver, ferrous lead, zinc and lead form immiscible layers and silver is distributed between them. Since the distribution ratio is about 300 in favor of zinc at 800 degrees Celsius, most of silver passes into the zinc layer. On cooling, the zinc layer an alloy of silver and zinc separates. The AgZn alloy is distilled in a retort when zinc passes over, leaving silver behind. The lead layer still contains unextracted silver. This is treated with fresh quantities of molten zinc to recover most of the silver. Fourth, confirmatory test for bromide and iodide. The salt solution is treated with chlorine water. Small quantity of bromine or iodine is thus liberated. The solution is then shaken with trichloromethane chloroform. On standing, chloroform forms the lower layer. The free bromine or iodine, being more soluble in chloroform, concentrates into the lower layer, making it red for bromine and violet for iodine. Fifth, determination of association. When a substance is associated or polymerized in a solvent A and exists as simple molecules in solvent B, the distribution law is modified as n root Ca upon Cb is equal to K, where n is the number of molecules which combine to form an associated molecule. Suppose benzoic acid is associated to bimolecules C6H5COOH whole twice in benzene and is present as simple molecules in aqueous layer. Then equation 1 can be written as follows, where n is equal to 2 minus root 2 C benzene upon C aqueous is equal to K. The concentrations in benzene and aqueous layer are determined experimentally. If the under root of the concentration in benzene divided by the concentration in aqueous layer gives a constant value, benzoic acid exists as bimolecules dimer in benzene. Sixth, determination of dissociation. Suppose a substance X is dissociated in aqueous layer and exists as single molecules in ether. If X is the degree of dissociation or ionization, the distribution law is modified as C1 upon C2 into 1 minus X is equal to K, where C1 is equal to concentration of X in benzene, C2 is equal to concentration of X in aqueous layer. The value of X can be determined from conductivity measurements, while C1 and C2 are found experimentally. Thus, the value of K can be calculated. Using the value of K, the value of X for any other concentrations of X can be determined. Seventh, determination of solubility. Suppose the solubility of iodine in benzene is to be determined. Iodine is shaken with water and benzene. At equilibrium, concentrations of iodine in benzene Cb and water Cw are found experimentally and the value of distribution coefficient calculated. Cb upon Cw is equal to Kd, but Sb upon Sw is equal to Kd, where Sb is equal to solubility in benzene and Sw is equal to solubility in water. If the solubility of iodine in water Sw is known, the solubility in benzene can be calculated. 8th, deducing the formula of a complex ion I3 negative. Some iodine is added to a solution of Ki and the reaction mixture shaken with benzene. A. The I2 in water layer can be found knowing the value of Kd determined separately and concentration of iodine in benzene determined by titration against thiosulfate. B. The total concentration of iodine I2 plus I3 negative in water layer is found by titration against thiosulfate. Knowing I2 from A, I3 negative can be calculated. C. The initial concentration of Ki taken is represented by equilibrium concentration I negative plus I3 negative. Knowing I3 negative from B, I negative can be found. Substituting the above values of concentrations in the law of mass action equation of the reaction in water layer, I3 negative upon I2 into I negative is equal to K. The value of equilibrium constant K can be calculated. If it comes out to be constant for different concentrations of iodine, it stands confirmed that the formula of the complex I3 negative which is assumed is correct. 9th, distribution indicators. In iodine titrations, the end point is indicated by adding starch suspension which turns blue. A greater sensitivity can be obtained by using what we may call distribution indicators. A few drops of an immiscible organic solvent such as chloroform or carbon's tetrachloride is added to the solution. The bulk of any iodine present passes into the organic layer and imparts intense violet color to it. So this was all about distribution law.